In this section, we will talk about discrete probability distributions. Recall that a random variable is essentially describing the outcomes of a statistical experiment in words. Discrete random variables are variables whose outcomes are countable. In this section, we will look at how do you assign probability to these outcomes. Now, in the case of discrete random variables, we can get probabilities from two ways. They could be based on data that we observe, we call those empirical probabilities, or they could be a mathematical function that describes those probabilities. But in any case, for a function to be considered as a probability distribution function, it needs to meet two properties. One, that the probability of any individual event that is possible from that random experiment has to be between 0 to 1. It cannot be outside of those bounds. And secondly, if we add up the probability of all the events that are possible, that sum will equal 1. So if a function meets these two criteria, we will call that as a legitimate or permissible probability distribution function. So first we look at empirical distribution. Empirical distributions are random variables where we observe some outcome. And then based on that outcome, we can calculate its expected value, which is the same as mean that we looked at, and then the variance as well. So for example, consider a departmental store, appliance store, which sells appliances. This table gives us the number of appliances sold in a period of 300 days. So for example, there were 54 days where the store didn't sell any appliance, but there were 72 days when they sold 2 appliances. So we want to look at the expected appliance sale. X column is what we're interested in. In the classical probability, we would have said that selling one appliance or 2 appliances or 3 appliances has equal probability. So like rolling a die, we said that each phase can come up with equal probability. But in empirical cases or real world cases, that may not be true as we see here. So to get the mean or the expected value, we first rewrite the frequency of sales, which is given by this column, into relative frequency terms. So here we are essentially dividing 54 by 300 and so forth, and we get our relative frequencies. And then we multiply our outcome with the relative frequency. So we are multiplying our number of sales with how often are those sales likely. So we get 0, we multiply 1 with 0.39, we get 0.39, and then so forth. And then we add this up, and this is our expected value or our mean sales. So unlike classical, where we just took the simple mean, here we have to take the weighted mean if the weights are given by the frequencies. And again, the denominator of a weighted mean, here's sum of all the frequencies, and as we said, they will add up to 1. To calculate the variance, we have to do a couple more calculations. So variance is defined as the summation of xi minus mu squared, which is our mean deviation squared weighed by the frequency. So it's again a weighted average of our second deviation, so our xi minus mu squared, and where the weights again are the relative frequencies. So to calculate that, we create a column where we subtract our x, which is our number of expected sales, with our mu, so 0 minus 1.5, and then we square it, would be 2.25. Then we can look at the next row. 1 minus 1.5 is minus 0.5, we square it, we get 0.25, and so forth. So this column is essentially this piece for each outcome, x minus mu squared. And then we weight it by the relative frequency. So here we are just multiplying our xi minus mu squared with our relative frequency. And then once we add this up, this 1.25 is our variance. And then the square root of variance is the standard deviation. So we can take the square root and we get the standard deviation. So this is how we use relative frequencies to get the expected value and the variance. Let's see how to implement this in JMP. Now we saw that earlier, so if we would go to analyze platform, we have a distribution option and we drag the variables here to get the summary stats. Now our variable of interest is our sales, but we do not want a simple arithmetic mean for it. We want its expected value. So we will make use of this option called frequency. We're going to drag our days to frequency and click OK. So now what we get is indeed our summary stats for our expected value. So here the mean, it is not the simple arithmetic mean that would have gotten by just averaging our sales. It is now the weighted mean where the weights are the frequencies. To obtain the variance, it's giving us a standard deviation, which we obtained before, but to get the variance, we can click on Customize Summary Stats, and then choose the option Variance as well. So when I click Variance, and the variance indeed is 1.25 as we had gotten before. So again, we'll make use of the frequency options in JMP to obtain weighted averages or expected values. In a business setting, we are often concerned about how two different variables may impact a third variable. So here, let's say we're manufacturing printers, and we have printers overall cost as a variable of interest, but the cost of printers is determined by two factors. One is the cost of parts, and then the cost of direct labor. So each row gives us the cost of different parts, and then the column gives us cost of labor. For example, there were 15 cases where our parts cost $85 and our labor cost $43. So our total cost was $128. So before we do any analysis with this bivariate distribution, we should convert these individual cells into relative frequency. So we know that there are 300 observations. We'll divide each cell by 300, and we will get relative frequency. So this will help us not only look at the individual expected value of costs contributed by parts and labor and the variances, but also a new concept called covariance, a relationship between these two cost components. So we'll look at covariance and correlation between the two series as well. So the first thing, as we said, was we divided our cells by the total count of observations. We had 300. So these cells are giving us the individual combination of 85 and 43, etc. And these column totals and row totals are very useful. We call these marginal probabilities. So 0.45 is the marginal probability of the parts being $85. Similarly, 0.4 is the marginal probability that a direct cost of labor was $45. We will use these marginal probabilities to get individual expected values of cost due to parts and cost due to labor. So we'll just illustrate it for one case. We would cast it into a single or univariate series where we have the marginal probability of getting $85 as parts cost is 0.45. And the marginal probability of parts costing $95 is 0.55. Can we apply the same method? We can weight these the cost by the frequencies, add this up, we get the expected value or the mean. Then we take the deviation of this mean of x from our mean, and we square it. So for the first one, we get 30.25, and then we get 20.25. And then we multiply these squared deviations from the mean with the relative frequency, 0.45, and we get 13.61. And then we add 13.61 with 11.14, and we get 24.75, which is the variance of the series given by the cost of parts. And then again, we can take the square root of this. We will get a standard deviation. Doing the same thing, we can also obtain our variance for labor costs. Said we with three options, and the variance for labor cost is given by 3.81. So now let's introduce the idea of a joint distribution. So let Z be the total cost, and we said that Z includes parts as well as labor costs. So we had 6 combinations, we add those up, we get these 6 possible cost values. And again, we are just reading off the frequency of each of these. So our cost being $128, the frequency is 0.05. So we can kind of do the same analysis. We get this new variable Z, which is combining or giving us our total cost. And we can apply the same steps and we get the expected value of Z, the total cost, as well as the variance of Z. Now, we will use this idea to get the concept of covariance. Covariance tells us the direction of movement of both X and Y, so our labor as well as our cost of parts. And the formula for covariance for a joint distribution is given by the variance of this joint distribution, which is 21.26, minus the variance of the first series minus the variance of the second series, and we divide this by 2. So in the previous slide we had obtained our variance as 24.75 of our parts, and the variance of our labor is 3.81. So we can subtract 24.75 and 3.81 from 21.26, divide by 2, we get a negative 3.65. So this tells us that we have a negative covariance. So when labor costs are high, we may be using a process where our parts cost is less. So there may be some little switch between labor cost and cost of parts. The correlation, which we visited earlier as well, gives us the association between these two variables, or the strength of the association, and it's given by the covariance, which we have gotten from the relative frequency method. Earlier we had got it from the empirical classical method and divided by the standard deviation of X and standard deviation of Y. And the covariance is minus 0.376. So this tells us that there's some negative association between labor costs and parts cost. It's not a very strong association, it's only 0.376. So let's see how we can do these calculations using technology. To do this, to get covariances and correlation in JMP is pretty straightforward, but notice that we have to make a slight adjustment. So our raw data was in a tabular form, but in JMP we have to kind of give it in a tidy form where instead of having this two-way table, we recast this into a frequency table where we first have our values of X, which is our parts, and then for each possible parts value, what are the potential labor costs that we can have? We can have 43, 45, and 48. So we just recast this table in this format. And then for the parts cost of 95, we have a labor cost of 43, 45, and 48 as well. And we're writing the relative, not the relative, the actual frequencies next to them. So that's all we need in JMP. We don't have to convert this into relative frequency. We don't have to do anything else. Now notice that these are the numbers we got using our tabular calculations for covariance and correlation. In JMP, we will go to Analyze Platform again. And here we will use a new tool, Fit Y by X. We are interested in Y by X has several options. We'll just get a simple bivariate. In this case, this also works when you have qualitative data, but here we have quantitative data as we have both our X and Y variable are in dollars. They're actually costs that we can expect from labor or from parts. So I'm going to move my X to X, my Y to Y, and we'll drag our count to our frequency like we did before as well. Click OK. And here, this kind of looks, it's just plotting our to cost, but in the red triangle, if we click on summary stats, this is where we in just one go get our covariance, our correlation, Our covariance is minus 3.66, and our covariance correlation is minus 0.37. And we also get the mean and the standard deviations of our x and y. Recall that for x, we had found that a mean was 90.5, and this is what we have here. And instead of variance, we get standard deviation, but if we square it, this number would equal 24.75. So again, JMP makes it pretty convenient, making sure that the data is cast in the right form to obtain joint distributions, covariances, correlations, as well as the individual marginal distributions as well.